Hello everyone, in this video we're going to learn about the polynomial functions and rate of change. Alright, so polynomial function is written as p of x is a sub n s to the n plus a sub n minus 1 s to the n minus 1 plus a sub n minus 2 times s to the n minus 2 plus etc. until a sub 0. Alright, a sub n is the leading coefficient. N is the whole number. And n is the degree of the polynomial. Alright, let's take a look at some examples. The following are examples of polynomials. P of x is 2 times s cubed minus 3s squared plus 11s minus 4. Or f of x is negative 2.3 s to the fifth minus 3.9 s squared plus 1.2. Right? P of x is just a number 7. P of x is 0. So these are polynomial functions. The following are not polynomial functions. So, for example, if you have r s is s to the 3.5 minus s to the 1.3 plus 1. If you have h of s is 3 to the s, or if you have k of s is 5s to the negative 2 plus 3s to the negative 4. Alright, so these are not polynomial functions. The first one because the exponent is not a whole number. This guy right here, not a polynomial function because this one is an exponential function, right? Where the base is 3, right? The last one right here, this is not a polynomial function because we have the exponent as negative integers. Now, given the following graphs right here, we need to identify which one is the polynomial function, right? Now, the first one right here, the function f right here, this guy is the polynomial function because it is continuous and smooth. So this is yes. This guy right here, the function h right here, this is continuous function and smooth. So this is a polynomial function. The function g right here is not a polynomial function because it has a sharp corners right here. The function k right here is not a polynomial function because it is not continuous at this point. Let's move on to the next example. Let's find the leading coefficient and degree of the polynomial functions. So for example, if I have the function f of x is 2s to the 4 plus 3s minus 5. Alright, so the leading coefficient I call LC is going to be 2, right? The leading coefficient right here is the coefficient in front of the variable with the highest power. Now, degree of this polynomial function is 4, right? The degree right here. Now let's take a look at the second example. For example, I have k of s is negative 12 plus 1 over 5 s plus 3s to the 4. Alright, so the leading coefficient in this situation is going to be 3 right here. And the degree is going to be 4 right here. Now let's take a look at the next example. For example, if I have g of s is 3. 3, I can rewrite this one as 3 times s power of 0. Keep that in mind, s to the 0 is going to be equal to 1. So basically 3, I just write this one as 3 times 1. But I will replace 1 with s to the 0. So that's why I get this one. Alright. So leading coefficient is 3, right? And the degree is going to be 0. Now let's take a look at the next one. A turning point is a point of the graph where the graph changes from increasing to decreasing or decreasing to increasing. A polynomial of degree n will have at most n minus 1 turning points. So for example, if you're not given a graph and you're given the function like this, y equals s cubed minus 3s squared plus 2s plus 1. Alright, so the number of turning points is n minus 1, which means n right here. Alright, so number of turning points is 3 minus 1 equals 2. Right? Alright, but if you're given a graph, where do you find the number of turning points? So you look at the graph right here. The function is increasing right here, and then decreasing right here, and increasing, and then decreasing. So the number of turning points is right here. The maximum, and the minimum right here. So we have 3 turning points in this situation. Alright. Now next one, we're gonna talk about a relative or local extrema. Now a polynomial function has a relative minimum or relative maximum where the polynomial switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. So in this situation, we have restricted domain right here. Alright, here's the local minimum right here, the first one right here, and the second one right here. These are lower points, right? So local minimums at s equals negative 4, right? When you project that, we see that s equals negative 4, and the second point right here, s equal to 0. So negative 4 and 0. Now, you need to know the difference between the local minimums at s equal how much and the local minimum values, right? So when we talk about the local minimum values, we talk about the y values at the local minimum point, right? So y value at the local minimum points right here is going to be negative 3, right? So we put negative 3 right here. And this guy right here, the y value is going to be negative 1. So we put negative 1 right here. Alright. Now, we're going to talk about the local maximum, right? Which means the higher points. So the high points right here, this guy and this guy right here. Which means negative 2 and 3, right? So we have negative 2 here and 3 right here. Now, the local maximum values, which means the y values of the local maximum point, right? So the y value, which means this guy right here, 2, and this guy right here, 1, right? So we have 1 and 2, right? Now, if the question asks you to find the local maximum points and the local minimum points, so you need to say the local minimum points are this guy right here, which means -4, -3, right? So you have -4, comma, -3, right? And then the second one is going to be 0, -1, right? So these are local minimum points. Now local maximum points is going to be -2 and 1 right here. So it could be -2, comma, 1. And the second point is going to be 3 and 2, right? 3 and 2. So keep that in mind. Now, we're going to talk about the absolute extrema. Another name of absolute extrema is global extrema. Okay. Up or local maxima, the greatest is called the absolute maximums. Alright, so we look at this one, local maxima right here, -2, 3, and the values is going to be right here, 1 and 2 right here. Alright, now they ask you absolute maximum, so which means they ask you the highest y values of the function, right? The highest y value of the function is going to be right here, 2, right? So 2 at x equals 3, right? So you need to be careful, right? Now, the list of all local minima is called the absolute minimum, right? Now, absolute minimum, which means they ask you to find the least y value of the function. Now, the least y value of the function is undefined because we look at the right hand side right here. We see the arrow right here, which means the graph keeps going down forever. So this one, none. Now, if I change the question, alright, I just erase this one. And I have restricted domain right here. So I put a dot right here, which means the graph can't be extended, right? So the least y values of the function is this guy right here, right? So this one is called the absolute minimum, right? Now let's move on to the next example. If we're given a graph right here, we need to find the relative minimum, right? So there is no relative minimum because the graph keeps going down forever, both sides, right? So this one should be none. Relative maximum right here, this is the highest point right here. So relative maximum as s equals 1, right? So we draw this one down, s equal to 1. Absolute minimum, there is no absolute minimums, right? So this one, none. Absolute maximum is going to be the highest point right here, which means 3. At s equals 1, right? Now turning points, we only have one turning point right here, which is the maximum, right? So local maximum values is 3. Local maximum points, which means 1, 3. Local minimum values, none, right? And local minimum points, none. Alright, let's move on to question B right here. Relative minimum. We have relative minimum is going to be right here. So it could be -2, right? At s equals -2. Relative maximum at s equals -4 right here. This is relative maximum and relative maximum right here. So -4 and 3. Absolute minimum is the least value of minima, right? So we look at this one because the graph keeps going down forever, so there is no absolute minimum. Absolute maximum is the highest value. This guy is the highest value, which means 2, right? At s equals 3. Now number of turning points, so we have this guy and this guy right here are turning points. So number of turning points are 2. Local maximum values. The local maximum values is this guy and this guy, which means 1 and 2, right? 1 and 2. Local maximum points, which means negative 4, 1. And 3, 2. Local minimum values right here, which means negative 3. Local minimum points is going to be negative 2, negative 3. Now question C. Relative minimum as s equals negative 3 right here and 3. Relative maximum at s equals this guy right here, the points right here, s equal to 0, and this points right here, s equals 5, and this points right here, s equals negative 4. Right, so we have negative 4, 0, and 5. Absolute minimum is the least value of the minima. Is the least y values of minima. So the y value minima right here, negative 3, and this guy right here, 0. The least one, which means negative 3. So we have absolute minimum should be negative 3 as s equal to negative 3 right here. Absolute maximum is the highest value of y of maxima. So the highest value of y of maxima is right here, 4. As s equals 5. There is 1 turning points, 2 turning points, and 3 turning points. So it could be 3 turning points. Local maximum values is this one is the local maximum right here, and local maximum right here. We find the y values, which means 4, 3, and negative 1. So we have negative 1, 3, and 4. Local maximum points. So we need to find the coordinate of these 3 points, right? So it's going to be negative 4, negative 1, negative 4, negative 1. The next one is going to be 0, 3. And the last one should be 5, 4, right? 5, 4. Now local minimum values, we have this guy is the minimum values, local minimum values, which means negative 3, and this guy right here, 0, right? So we have 0, negative 3. Local minimum points is going to be the coordinate of the local minimums. So it's going to be negative 3, negative 3. And 3, 0. Right? Now let's move on to the next one. between two real zeros of a polynomial, there must be at least one local maximum or local minimum. Polynomials of even degree must have either a global maximum or a global minimum. Now look at this example right here. For what values of x is p of x is equal to 0, which means we need to find the 0 of the polynomial functions. So we have the first 0 right here, the second 0 right here, and the third 0 right here, which means negative 4, 1, and 4, right? Negative 4, 1, and 4. The minimum values as x equals about negative 2.5. And this guy right here, about 5.5. For what values of s does ps attain local maximum? So local maximum is going to be right here. So it's going to be about 2.5. Now for what values of s does ps attain global minimums? So we look at this one right here. Polynomials of even degree must have either global maximum or a global minimum. So we look at this one, we see that the graph has the same end behavior, which means the graph has an even degree, right? So this guy has global maximum or global minimum, right? In this situation, we have the global minimum, which means right here. So s equals negative 2.5, right? Now let's talk about the points of inflection. A point of inflection occurs when a function changes from concave up to concave down, or from the concave down to concave up. Function has the shape like this. Or if you cut this one in half and you have the left half, it's going to be like this, or the right half, it's going to be like this. The function is called concave up. If the function has the shape like this, or if you cut this one in half and then function becomes this guy and this guy, this is called concave down. Alright. Now, a point of inflection. At a point of inflection, the rate of change of the function changes from increasing to decreasing, or from decreasing to increasing. Alright. So we look at this example right here. The graph g of x is shown in the figure above. Use the graph of g to answer the following. Find any values of x where the function g has a point of inflection. Alright, so we look at this one right here. The function changes from concave up to concave down right here. Right, and the point of inflection is going to be right here. Now the function changes from concave down to concave up. And then the function has the point of inflections right here. Alright, so the point of inflection occurs as s equals negative 1 and 1. Right? And if the question asks you what is the coordinate of the point of inflection, you need to say that -1 and -1 right here, right? The second point is going to be 1 and -1, right? Right here. Alright, question B. For each of the following intervals, determine if the rate of change of the function g is increasing or decreasing. Explain your reasoning for each answer using features of the graph of g of x. In order to know if the rate of change of the function is increasing or decreasing, we're going to draw two tangent lines. Alright, now we're going to use the Christmas tree trick. Alright, if the lines go in this way, the slope is positive. If the lines go in this way, the slope is negative. If the lines go in this way, the slope is 0. If the line is vertical, the slope is undefined. Now on the left hand side right here, if the line is steeper, the slope is bigger. Now on the right hand side, if the line is steeper, the slope is smaller. Steeper line, smaller slope, right? Alright, so we have two different ways to do this problem, right? The first one, we can use the concave, right? Because the graph is concave up, the rate of change of the function is increasing, right? So this one is increasing. Or you can draw two tangent lines and you compare the slope of two tangent lines. Now question B. -4, -3. So -4 and -3 is going to be this one right here. Okay, and you see that the function is concave up, right? And the rate of change is increasing. Now, in order to use this Christmas tree trick, we're gonna draw two tangent lines, right? So we're gonna draw the first tangent line right here and the second tangent line right here. And we see that this line right here is steeper than this one, right? So look at this one, it's gonna be on the right hand side right here. Steeper line, smaller slope. So for example, the slope of this one is -5 and this guy -3. So in order to get -3 from -5, which means we're gonna add -2, right? So the rate of change is increasing. Now let's move on to question C. -1 to 1. Alright, -1 to 1, which means this guy right here. Alright, and you see that the function is concave down. Because the function is concave down, the rate of change is decreasing. Alright, another way to do this one is to use the Christmas tree trick right here. We're gonna draw three tangent lines of this. So the first tangent line right here, the second tangent line is right here, and the third tangent line right here. Now, the tangent lines go in this way, the slope is positive, right? This is positive. The tangent lines go this way, the slope is 0. And the last tangent line is gonna go this way, the slope is negative, right? And you see that the rate of change changes from positive to 0 and to negative, right? Which means the rate of change is decreasing. Now the last one, question D. Interval 1 to 2. So 1 to 2, which means this one. Alright, look at this one, we see that the function is concave up. So because the function is concave up, the rate of change is increasing. Again, we can use the Christmas tree trick right here to determine if the rate of change is increasing or decreasing by drawing two tangent lines. So the first tangent line right here and the second tangent line right here. Alright, and you see that the tangent lines go in this way, which means on the right hand side right here. Alright, steeper line, smaller slope. We look at this one is steeper than this guy right here, which means the first tangent line right here has smaller slope than this guy. In other words, the rate of change is increasing. Let f of x be a polynomial function with the given values. Are there any guaranteed extrema? If so, state where they occur. Alright, so we need to find two zeros, right? We learned previously, if you have two zeros of a polynomial function, then there must be at least one local extremum between the two zeros, right? So we need to find two zeros. So we look at this one right here. We have two zeros right here, right? This one not the zero, this one doesn't count. Look at the right hand side, 0, 0, which means x equal -1 and sit right here. So we have two zeros right here, so we say yes. And the local extremum occurs inside the interval -1 to 6. Alright, but we don't know if this guy is the local mean or local mass. Now look at number 8 right here. We look at two zeros, so we have this guy right here and this guy right here. So we say yes, there is at least one local extremum between 6 and 10, right? Now look at this one, we only have one zero right here. Alright, this guy not a zero, this guy not a zero. So because we only have one zero, there is no guarantees extremum. So this one should be none. Now let's move on to the next questions. Is there a global maximum or minimum for each function? The function must be even. And when the function is even, they have the same end behavior. If the leading coefficient is positive, the end behavior going up like this. If the leading coefficient is negative, the end behavior going down like this. Alright, and keep in mind they must have the same end behavior, either going up or going down. Right? Now we look at this one right here, we see that the leading coefficient is positive. And the highest degree is 8, which means even power. So, yes, there is a global minimum, right? It's gonna be like this. And global minimum is gonna be right here. Now let's take a look at number 11. This guy has even power and the leading coefficient is negative. So we're going to use the second case right here. So it looks like this. So yes, we have the global maximum. Now we look at the next one, number 12. This guy has the highest power right here. This is the odd degree, which means it doesn't have global maximum nor minimum. Now look at number 13, the highest degree is going to be 6, so this is even, and then the leading coefficient is -4. So we're going to use the second case right here. So it's going to be like this. So this guy has the global maximum. Now let's take a look at the last example. Find the following extrema. Now question number 14, absolute minimum of. Absolute minimum is the least value of the minima, right? So none, right? Because this guy keep going forever, even though this is local minimum. So this guy none. Question 15, absolute maximum of 2 right here, right? The highest point right here. So this guy 2 when s equals 3. Relative minimums at this guy right here is the relative minimum. We only have one relative minimum, which means at -1 right here. Relative maximum as we have this guy as a relative maximum as -4 and 3 right here. -4 and 3. Now number 18, absolute minimum. There is no least value because this guy keep going down, right? So there is nothing. Now number 19, absolute maximum. We have the highest point right here and the highest point right here. So absolute maximum of -1 when s equals -5 and 1. They have the same y value. Relative minimum is right here. It's going to be -3, right? Relative maximum is -5 and 1 right here. And the last one, absolute minimum is this guy right here. So it's going to be -6 when s equals -5. Absolute maximum is right here. It's going to be 3 when s equals -2. Relative minimum is going to be this guy and this guy right here. It's going to be -5 and 2. Relative maximum is going to be this guy right here, -2, and this guy right here is going to be 4. And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand